This week we will focus on rectifiable and unrectifiable sets. So the definition of a rectifiable set is as follows. A subset A of Euclidean space is M rectifiable for some integer m if there are Lipschitz mappings f sub I from Rm into Rn whose union, the union of their images, covers Hm almost all of the set A. So rectifiable sets are sort of measure theoretic analogs of smooth manifolds in a couple of ways. So for example, these Lipschitz functions f of I serve as sort of chart maps to our set A. Although instead of them being smooth chart maps, they are instead just Lipschitz. So instead of being differentiable, they're just almost everywhere differentiable. And instead of covering the whole surface, they just cover the surface up to a set of measure 0. And moreover, rectifiable sets don't need to be surfaces at all. They could be totally disconnected. Furthermore, they have a almost everywhere tangent structure, similar to manifolds, however, in a weaker measure theoretic sense that we'll make more precisely later. One of the benefits of working with rectifiable sets is that they have nice stability properties in the sense that if you take a countable union of rectifiable sets, you get another rectifiable set. And also they're stable under Lipschitz mappings. So the Lipschitz image of a M rectifiable set will be another M rectifiable set. In practice, it's easier to establish that a given set is a rectifiable set than a smooth set. So as we'll see in later videos, there are some nice geometric lemmas that tell you when for example, a subset is contained inside a Lipschitz image of Euclidean space. Now, sufficient conditions for when a set is contained inside a smooth image of Euclidean space, while there are such conditions, they are a little harder to establish in practice. And finally, many results that are proven for smooth manifolds extend to rectifiable sets. So for example, Rademacher's theorem holds for Lipschitz functions defined on rectifiable sets, not just on Rn. And also in some cases, rectifiable sets are sort of the exact amount of regularity for a certain result to hold. So in the sense that there may be a result that held for smooth surfaces and then you proved it for rectifiable sets, and actually you can't weaken the conditions any more than rectifiable. So this makes more precise the comment I made on the previous slide of what I mean by having an almost everywhere tangent structure. So by that I mean in terms of tangent measures. So suppose I have a subset A of Euclidean space, a finite m-dimensional measure. Then it's M rectifiable if and only if at almost every point in A, the set of tangent measures of Hausdorff measure restricted to the set A are all flat and the lower densities are positive. Now, if either of these two conditions hold, in fact, not only are the set of tangent measures flat, but there's actually just one flat tangent measure at each point. Or in other words, at almost every point A, there exists a tangent plane, an m-dimensional tangent plane v sub x, so that all tangent measures of Hausdorff measure restricted to A at the point x are just multiples of this flat measure. So notice that this is different from the usual notion of a tangent plane. Usually when we think of, for example, a smooth surface or the graph of a smooth function, we think of a tangent plane as a plane where as we start zooming in on our set, our set looks more and more like the plane in terms of Hausdorff distance, like it's getting much, much closer to looking like a plane. However, rectifiable sets don't have to have as strong a tangent structure as this. So as one example, suppose we define a set E that's equal to, so first of all, let's enumerate the rationals by some sequence Q sub I. And then let E be the union of the boundaries, or circles, sent at radius qi of radius 2 to the minus I as a subset of R2. Okay, so notice that each of these circles is a smooth curve and hence is going to be rectifiable because we can split it up into a union of Lipschitz images of an interval in R in the real line. And so now, by definition of rectifiability, any countable union of such sets is going to be rectifiable. However, this set is not going to have tangents in the usual sense because this set is actually dense in the entire plane. However, if we however, it still has a tangent structure in this weak sense with respect to tangent measures. So what that will mean is that at almost every point in the set E, as we start zooming in on it, our set will start converging around a line or a plane, not in the Hausdorff sense, but in a measure theoretic sense. The measure will start concentrating around the plane. Now, the counterpart to rectifiable sets are unrectifiable sets. So a set is purely M unrectifiable if the Hausdorff m-dimensional measure of A intersected with any Lipschitz image of Rm is 0. So this should be Rm into Rn. Okay, so what does such a set look like in practice? So we've already seen one example, so the Garnett example. So recall that this is a one-dimensional set of positive and finite measure that's totally disconnected. And it turns out that this set will be purely unrectifiable. And you can see that because if you zoom in at almost every point in the Cantor set, as you blow up, you're just going to see more and more copies of the tangent of the four-corner Cantor set. And in particular, none of those are flat at all in any sense. And so so that will mean that the set of tangent measures is just going to be measures containing copies of the Cantor set. So in particular, none of the tangent measures are going to be lines, and so the set can't be rectifiable. Now, notice that in the definition of being purely unrectifiable, there isn't a restriction about the size of the measure, about whether it's finite measure or not. And so you can actually show that the boundary of the von Koch snowflake is also purely unrectifiable, even though the dimension of this curve is actually strictly bigger than 1. The Besicovitch decomposition theorem says that given any subset E of Euclidean space with finite m-dimensional measure, where m is an integer, I can decompose E into a disjoint union of a m-rectifiable set and a purely m-unrectifiable set. So the proof of this is not too bad. So what I do is first I pick F1 contained in E, m-rectifiable, such that its Hausdorff measure is at least 1/2 of the supremum over all Hausdorff measures of m-rectifiable subsets of E. Okay, so notice that this supremum could be 0 and the Hausdorff measure of F1 could be 0, but that's fine since a measure 0 set is trivially rectifiable. Okay, so then what I do is I pick F2 contained in the remainder of E outside F1, again rectifiable, such that its Hausdorff measure is at least 1/2 the supremum of the Hausdorff measures of rectifiable subsets of E minus F1. F is m-rectifiable. Okay, and then I keep doing this. So I'll find the set F3 that's rectifiable in the complement of the union of F1 and F2 inside the set E, whose measure is at least 1/2 the supremum over all such sets, and so on and so forth. And then my final subset I define to be the union of all these sets that I find. So because each one of these sets, Fi, is rectifiable, the set A will be rectifiable as well. And then you can show by the way that we pick these sets that if I define B to be the complement of A in E, that this will be M purely unrectifiable, or purely M unrectifiable. What make rectifiable and purely unrectifiable sets interesting geometrically is the dichotomy that occurs between their different properties. So, for example, we have the Besicovitch-Federer projection theorem that states the following. So let's suppose we have an HM measurable subset A of finite measure. Then A is purely M unrectifiable if and only if the Hausdorff m-dimensional measure of its orthogonal projections are 0 for almost every m-dimensional plane. Furthermore, we have that A is not purely m-unrectifiable, so that is to say it contains a non-trivial rectifiable subset if and only if its Hausdorff if and only if its orthogonal projections into almost every plane have positive m-dimensional measure. So notice that these two statements aren't negations of each other. Okay, so a couple of things to observe. So first of all, rectifiable sets, even though the above statement says that if you're rectifiable, then the Hausdorff measure of your orthogonal projections are almost always positive, you could still have a rectifiable set whose orthogonal projections were 0 in some direction. So for example, if you look at a straight line segment, okay, this is clearly rectifiable, and its projections in most directions are positive, but if you project in the direction parallel to this line segment, you get a singleton point, which of course has measure 0. Similarly, a purely unrectifiable set, so even though the above theorem says that purely unrectifiable sets have measure 0 projections in almost every m-dimensional plane, they can still have positive measure projections in some directions. So, for example, the four-corner Cantor set that we saw earlier, there is a particular direction where if you project the set in that direction, then its set is actually an entire interval. So this is an example of a purely unrectifiable set whose projections are non-trivial in a few set of directions. However, for almost every other direction, the orthogonal projection will have one-dimensional measure 0. And finally, so remember from our discussion of Falconer sundials that it is possible to construct a set A where it has measure 0 projections in a positive measure set of planes and has positive measure projections in a positive measure set of planes. Okay, but that doesn't contradict the above theorem. The above theorem would then imply that such a set would have to have infinite m-dimensional Hausdorff measure. So to sum up, the Besicovitch-Federer projection theorem, what it says is that purely unrectifiable sets and rectifiable sets, there's this big gap between them. If you are rectifiable, then almost all of your projections have positive measure. And if you're purely unrectifiable, almost none of your orthogonal projections have positive measure. And there is no in-between between rectifiable and purely unrectifiable sets. Finally, I'd like to end this video by saying, though our focus is mostly on rectifiability of sets, we can extend the definition of rectifiability to Radon measures. So we say that a Radon measure is m-rectifiable if it's absolutely continuous with respect to m-dimensional Hausdorff measure, and almost all of its support can be exhausted by a countable union of Lipschitz images of Rm. And we say that a measure is purely m-unrectifiable if every Lipschitz image of Rm has mu measure 0. So we state this definition just because for some of the results that we'll encounter later, it'll be a little bit more convenient to state them in terms of rectifiable measures versus rectifiable sets. In fact, we can get slightly more general results that way.